Perfect. Yeah, it really could not have gone better. Hello Internet, my name is Quinn and this is Blondihacks. I'm back on the big steam engine project this week and it's time for lubrication. Now what's cool about this engine is that it's big enough that I can start to make some details that you would see on full-size engines. Really cool things like, glass oilers. I've always wanted to make a set of glass oilers. They're not in the plans for this engine. It just specifies plain old oil holes in the crosshead bore, but there's plenty of room to make some glass oilers, so I'm going to do that right now. I modeled this up in CAD to start with because there's no plans for oilers like this in the kit, of course. If you want to make these oilers yourself, the plans and models are all available on my Patreon, and you can scale them up or down for different engine sizes. These would work for any steam engine or hit and miss engine or any other type of engine that uses a total loss oiling system. I'm going to start with the most difficult thing, which I think will be the glass. I ordered this cheap set of 8 test tubes on Amazon. As you can see, one of them didn't survive shipping. A moment of silence for the fallen. All I have for cutting attempts is this basic hardware store glass cutter, the type that we all have that doesn't really work and yet we all keep buying them, but I'll see if I can make some progress with it here. I'm going to do some test cuts here to figure out my process. I've got this fixture of sorts rigged up here to try and get a nice even scribe line all the way around the tube there. And that certainly worked well. I got a nice clean scribe at a consistent height there all the way around. It's a little bit on the light side, but I'll try. There are 127,000 YouTube videos on how to cut glass. I know because I watched all of them. And I'm going to try various techniques from those videos, one of which is the candle and ice method. So I've got a candle here. I chose ruby persimmon. This choice is very important because it will dictate how your shop smells when this job is done. The idea with this method is that you thermally stress the glass right on that score line that we made. So we heat it up with the candle and then cool it with the ice, and you do that back and forth, and apparently the thermal stress will cause the glass to fail right on the scribe line. Now, this is the method that we all used in grade school to make arts and crafts projects from wine bottles, and it certainly works extremely well there. However, with these little test tubes, it didn't work at all, at least not initially. I went back and forth a couple of times, but honestly, as soon as I touched it with the ice the first time, I got stress fractures all over the area there, and it did eventually crack there, as you can see, but the joint is an absolute disaster. There's stress fractures all over the area, and it didn't split anywhere near my scribe line. Undeterred, however, I knew my scribe line wasn't very deep, so I thought I'd give it another shot, and I made a much, much deeper score there. And I gave it another try with the candle and the ice. Now I should say that I'm following the examples that you see for wine bottles with the fire and ice, and they involve quite a lot of heating and then basically one pass with the candle. And again, as soon as it touches the ice, you just get a hot mess of stress fractures everywhere. In fact, this joint failed after just one pass on the fire and ice, so clearly no good there. Because the glass fails so dramatically as soon as the ice touches it, I thought maybe I was thermally stressing it too much. So I did another test here with a deep score line and doing very light passes with the heat and the ice, just one loop with the candle, going back and forth many times. And that actually worked quite a bit better. You can see most of the cut is on my scribe line there, but again, I do have some fracturing there below the line as well. So it was close though, so I gave it a couple more tries, and I got a couple of good results. This is probably the best one. No fracturing here, but again, not really all the way around on my line. But this is showing promise. However, after a few more tries, you can see that I still get stress fractures probably half the time, and it just really wasn't working out. I did several attempts at this gentle scribing and heating and cooling method. Since I wasn't getting clean breaks on the scribe line, I thought maybe my scribe lines aren't good enough. So I took some very careful measurements of the test tube here to try and get an exact internal diameter for it. And then I went over to the lathe and made a quick and dirty fixture for holding these test tubes to hopefully use the lathe to create the perfect score mark. I turned the mandrel down a little bit undersized to leave room for some tape, and that gives a nice firm grip on the test tube, but still allows you to slide it on. That seemed to work pretty well. Next, I mounted the glass cutter in my tool post, which is easy because they have a square end on them, and I figured I can just ease this guy in very slowly into the test tube to create a perfect score. Now, as you can see, these test tubes are not particularly round. In fact, they're as much as 10,000ths out of round, which is quite a bit for this situation. But I was feeding in extremely slowly, like a tenth per revolution, basically as slow as I could stand to turn the hand wheel, because if you go even a little bit fast, it's going to dig in and the glass is going to shatter. Doing this, I did manage to get a very consistent scribe line all the way down, and I thought, well, what happens if I just keep going? Because it's kind of working. So I just kept going. I was feeding in very, very gently, again, as slow as I could stand to do it. But glass cutters aren't really intended to be used this way. They have kind of a depth limit on them. And if they get in a little bit too deep, well, that happens. So the glass shatters as soon as the wheel starts to dig in slightly more than it's designed to do. But I did have success there before I got greedy. So let's try again, just aiming for the scribe line. But this time, honestly, as soon as the wheel touched a certain part of the tube, it shattered. And I tried this a couple more times, and I could never replicate the success of that first one. Every other attempt, the glass shattered at some random point during the scribing. And this is really just down to the fact that these tubes are not round enough to do this. Being 10,000ths out of round is enough to where you just can't get a consistent amount of pressure all the way around the glass. Maybe if you could rig up some sort of spring-loaded holder for the glass cutter, this would work, but that's more work than I want to try here. The next method I thought I'd try is a classic for smaller tubing, which is to just make a nick with a file that you don't care about. Emphasis on don't care about, because filing glass is a very quick way to dull a file. And then once you've got that little imperfection on one side, you just put your thumbs on the opposite side and you pull the tube kind of apart and towards you at the same time, putting firm pressure opposite that imperfection with your thumbs. There are many, many thousands of videos on YouTube making this look very, very easy, and I have never actually gotten this to work. Not even on small tubes, honestly. I don't know why. I put far more pressure on this than was probably wise and couldn't get it to snap, so I tried it again with a full score mark all the way around this time, using the previous technique that worked quite well for that. But again, no snappy. Alright, one more Hail Mary for this method. I'll use the vise to create a sharper fulcrum right at the score line there. So the vise is not squeezing the tube, it's just close enough on the tube to give it a firm grip and give me, as I said, a sharp fulcrum. And, well, yeah, that was predictable enough, I suppose. So much for that plan. Okay, time to get serious. I've got a fixture plate here with a setup that will hold the tube fairly snugly at a fixed distance from the edge of the plate there and allow me to rotate it smoothly. And I'm marking the length that I want for my tube section. Then I rigged up a sort of cross slide of sorts with a square there and a V-block, and I've got the Dremel in that V-block with the diamond cutting wheel on it. And I set that right on my mark there, and then I tape that to the V-block just to keep it from sliding in and out. And then I start moving this towards the cut. Now this is a technique that I did see in another YouTube video and it worked well for him, so I thought I'd give it a try. And this seems to be working quite well. I'm moving the Dremel towards the tube, again, basically as slowly as I possibly can. I'm not even putting pressure on it. I'm just kind of thinking about moving it towards the tube and turning the tube as I go. And would you look at that? I had one little chip there that fell right off, otherwise a perfectly clean cut, certainly within sanding distance anyway. I'm very pleased with that. And in fact, this setup should even repeat, so I put another tube in there. I'm using fresh tubes each time because I want the factory end on one side. But in fact, these tubes aren't very consistent in length, it turns out, so I did have to adjust my setup between tubes to get the saw on the mark. But I did it again, and it worked the second time. Well, actually it worked the third time. I had 2 out of 3 successes with this method, but compared to total failure with the other methods, a 67% yield is pretty darn good. To clean up those ends, I thought I'd try flame polishing, which is another technique for glass that the internet makes look very easy. And this does work really well. As you can see, the end is all nice and rounded over and shiny. It looks really nice, but you can also see I've got a giant stress crack all the way down the back there. And I tried a bunch of practice pieces and I got a stress crack on almost all of them, so I'm sure this works. Probably my torch was too hot for this thin glass, but I just didn't want to take the chance on these really hard-earned pieces that I've created here, so I just went straight to the sandpaper. I started with 120 grit, and that really cleans up all the rough edges, as you can see. And then I went to 400, first dry and then wet, a little bit of water on there. And after this, the edge is completely soft to the touch. There's no hint of any sharpness there at all. It's not rounded over and shiny like a flame polish would be, but it's a very nice edge. And this is all going to be under a flange anyway. What I especially love about this technique is that the results are very accurate. As you can see, I've got these two tubes here now, and they're both within 3/1000ths of the dimension that I was aiming for. In fact, they're both a little on the large side, so I could even sand those down to really nail that dimension. A lot of the glass cutting techniques you see online, they work, but they don't particularly care where the break ends up, at least not to machinist level of parts tolerances. Well, here's the wreckage from all my attempts. Many test tubes died in the making of this. I got the two pieces that I needed, so their sacrifices were not in vain, though I'm sure that's cold comfort to other little test tube families. Okay, let's get to the machining now, which should be all very straightforward. I'm going to start by making the top caps for my two oilers. I'll face the end off of this scrap, as is tradition. There was already a hole in it, which I will use as the guide to drill this out for the clearance hole that goes through the top of the cap. Then to start the counter bore, I'm going to use a trick I like very much, which is to use an end mill holder in your tailstock. And I put an indicator on that, preloaded up more than the depth that I need to get a very accurate depth. This is a 2-flute center cutting end mill, or a slot drill as the Brits would call it. And that allows you to plunge straight into the material if you run the lathe nice and slow. And this gives you a really great start for the boring bar. Note that this does not make a flat-bottomed hole. End mills have clearance angles on the ends of them, so you end up with a bit of a positive cone in the bottom. But that's okay, we can flatten that out with the boring bar and then proceed to bore this out to dimension. In with the boring bar now, I started by bringing the diameter out to within finishing cut range of the final diameter, but I don't want to finish it just yet. Then I'll deburr that. Just make sure that I'm not too big there. I'm within striking range of final diameter, but not quite there. And then I will flatten out the bottom and bring the depth to dimension. The diameter is much more critical than the depth, and when I'm doing a counter bore like this, I like to do the most critical dimension last. I find I make fewer mistakes that way. So I'll double check that I'm at depth here, and again, the tolerance on the depth is generous, so not too fussy here. And then I should be able to do the final cuts here on the diameter. Now, because these tubes aren't very round, I'm actually doing this by trial and error, just taking very light cuts a little at a time and test fitting until the tube seems like it has a nice fit there. And that's really good right there. While I'm here, I also want to sanity check the depth with an O-ring here. The top of the oiler doesn't actually have an O-ring in it, but the depth of the cap is the same on the bottom. So if this depth needs to be different, I want to know now. But that looks really good, actually. Got good coverage on the glass with the O-ring in place, so I'll proceed to turn down the OD now. This, of course, is not a critical dimension, but, you know, got the micrometer out, might as well use it. Make the noise. To part this off to length, I'm finding the edge there of the parting blade with my scale, and then I translate down using a dial indicator on the carriage to just the right depth. Start that part, and then go in there and put a fairly generous chamfer on the corner there, because that's going to be the visible part of the oiler. And Yahtzee. A little bit of deburring and such, and there is the final cap. One more test fit on the top of the glass there, and that is looking really good. I think that will work nicely. So now I go ahead and make the bottom cap, which is identical, so I'm not going to show it again. The only difference is the bottom cap is a little thicker, and it has a threaded hole in it, as you can see here, instead of a clearance hole. The bottom cap also has a slightly smaller counter bore because the flame polished factory top edge makes the diameter of the tube larger at that end. Not a lot, but just enough to where the caps cannot be identical. And there's the two caps. You can see the bottom one is thicker because it needs room for those threads in there that hold everything together. And that is looking very good. Now I need two of these oilers, so of course I made all those parts twice, as you can see here, and those are looking the part. Next is a thin bar that runs down the center of each oiler. This holds everything together and also acts as the delivery mechanism. So I start by center drilling and drilling a very tiny hole quite deep into the end of the part. Let's do a quick concentricity sidebar on this next step because I get a lot of questions about this exact situation. Is it okay to center drill and drill with the stock choked up in the chuck like this if you are then going to be pulling it out and doing other operations? The answer is it depends. If you do the operations in this position and then pull the stock out, you will lose some concentricity. Now, whether that matters or not depends on what else you're doing. If you're going to be turning the stock down sufficiently that you're going to overcome any loss of concentricity that might be coming from your chuck jaw position changing and any imperfections or bends in the stock, as I'm doing here, then it doesn't matter. But if, for example, the piece was already finished or was precision ground stock, something like that, where you needed the outer surface to remain concentric to the features that you're creating in the end there, then you have to do it pulled out with a steady rest. Doing these steps with the stock pulled out from the steady rest is the better practice, so if you're unsure, just do it that way. This hole is actually the metering orifice for the oil. So this is a 40 thou drill. It's the smallest drill I have without getting into the PCB drills. So I'm drilling this very carefully because my lathe won't run fast enough for a drill this small. Here's a Swarfy the Duck for scale, so you can see how small this drill really is. I'm starting with this size because this is, I think, going to be a little on the small side based on previous engine oiling systems that I've built, and then I can enlarge it from here if the oil feed rate is too low. Then I turn the OD of this bar down quite a bit. This diameter isn't critical, but the smaller it is, the more capacity the oiler has. But it also needs a sufficient shoulder on the bottom to seal the center post around the bottom cap there so the oil doesn't leak. And then there's a shoulder area at the bottom with a thread. Then I'll mark the length of the center section, and there's a narrow diameter at the top for a thread as well, which I'll do in the same setup here with the grooving tool. I'm stopping short of my scribe line there, as you can see. And then I can measure the length of that shoulder and then use a dial indicator to come in the required amount to finish it off to exact dimension. And we're within 1/1000th there, so that's good. That dimension is fairly important because it has to match the glass and have just enough compression on the O-rings to seal everything up. Then a thread on the end, and Yahtzee. I need a thread on the other end as well, so I just flip that around with some aluminum shim to protect the work from the jaws, and put a thread on there as well. Over to the mill now. This part needs a cross hole right at the base here, so I'll center up with the edge finder. This is the rest of the plumbing here. So I'll center drill with my number 1 center drill, which is bent. That's an awesome quality in a center drill, really helps with accuracy. And then I'll drill that straight through. This drill is double the size of the orifice because I don't want anything besides the orifice to govern the rate of oil flow, so all other holes are larger. And you can see how the two holes meet up there. So the cross hole feeds the oil into the center channel and then down into the plumbing below. Here's a little mock-up here with the 2 O-rings in place to seal the bottom there against leakage. And then the top does not have an O-ring so as to avoid creating an airlock there at the top, which might prevent the oil from draining out. Speaking of plumbing, I do need some of that. So once again with this small round bar, I will face off the end, put a center drill in there, and drill this all the way through because we're creating a pipe here. Once again, this drill is twice the size of the orifice in the oiler so that nothing besides the orifice will influence the flow rate of the oil. And there's a thread on this end that threads into the crosshead bore on the engine. So I'll match the thread that the engine has there. This pipe needs to have a 90-degree bend in it, so after doing this long piece that you see here, I can part this off. The length is not super critical here, so I'm just using the scale. And then I create a second identical piece that's shorter, and that will be the 2 pieces of plumbing. As you can see here, the hole didn't quite go all the way through, which is a common problem because I always try to get the hole just the right length so I don't ruin too much of the stock on the far side, but didn't quite make it there. This is an easy fix, just put it back in the chuck with some shim stock and run the drill through until it breaks through. You don't have to worry about concentricity here because the drill is going to follow the existing hole. Over to the mill now, and I'm setting up to miter these 2 pieces so that we can create the L-shaped pipe out of them. I've got a little square there to get the 45-degree angle, and the part's being held by an aluminum V-block that was part of a fixture I made many years ago, and I've kept it around because it's really useful for tiny setups like this. With that part sitting at 45 degrees, I just mill it down until the flat spot I'm creating meets up with the outside corner of the pipe there. And then I do the same thing on the little piece. To complete the L-shaped pipe, I've got my jewelry fixture plate set up here for silver soldering the two pieces together. So I'll get some flux on there. I try not to get any flux in the center hole there, otherwise the solder will flow in there and plug it up. It may do that anyway, as is often the case. And then come in with the heat. This is a pretty small torch I'm using. It's one of those yellow MAP gas torches from the hardware store, but I've got it turned way down because these parts are very small. And once the flux turns watery, then I go in with the solder, and then I make sure to heat it evenly from a bunch of different angles to make sure that the solder flows all the way around, because the solder will go to wherever the heat is. Let that cool down a bit, and then into the pickle bath it goes. That's Sperex number 2 pickling acid. Let that sit in there for 5 minutes, and then into clean water to rinse it off and stop the reaction. And that'll get all the flux and residue from the silver soldering off. And then a little blow test to make sure I didn't plug up the hole. If I did, no big deal, just run a drill gently in there to open it up again. Then to clean up all the discoloration on the brass from the silver soldering, I use the Scotch-Brite wheel and a little bit of work with some needle files to get into the areas where the wheel there can't reach. This always does a really nice job. There's the final result of the cleanup. It's a pretty decent solder joint, I think. It's not perfect, but I'm fairly pleased with it for such a small part. This could also be soft soldered. I honestly couldn't find my soft solder. Now the cool thing about model engineering is that it's not enough for the parts to look nice, they have to actually work. So let's mock things up here. I've got enough parts to actually test this oiler and see if it's going to function as a tiny drip oiler. So I'll fill it up here with just a little bit of oil because I want the most difficult test, which is not too much of a pressure head on the oil. And I want to make sure that the oil is actually going to drip out of that pipe at the end there with a minimal oil level in it. And sure enough, after a few seconds, I got a drip. And then about 6 or 8 seconds later, I got a second drip. I'm getting one drop about every 5 to 10 seconds, which is really honestly just about right. That's about what I was hoping for. It could even be a little bit slower than that. The engine really doesn't need that much oil, but I'm happy with that. Next, we got to get the alignment right on this pipe, which is always tricky with fixed plumbing fixtures like this. First, I'll thread it in and see where it lands. And of course, it's exactly opposite of where I want. Never fails. So the next step is just to experiment with copper washers of varying thicknesses until it lands in the correct orientation when it's tight. And then if you don't like the look of the copper washers, you can measure what you ended up with and make a little brass bushing to match. So let's do a test fit on the engine here, get some oil in there, and let's see if they actually work to lubricate the engine. I'll put a nut on there to hold the top cap in place. And that's looking pretty good, but I say nuts to those nuts. Those are not going to stand. Back to the round bar, and I'll make some decorative finials to replace those. I put a threaded hole in the end of some stock here, and I basically just experimented with round nose and angled tools until I found kind of a pattern that I liked that was easily repeated, so the two come out the same, and I landed on a flat section with a large radius above that, and then finishing off with my normal turning tool, but using it as a parting tool to create a pointed top there. And there we go. I can replace those ugly nuts with some nice little finials. The other advantage of those finials is that they're smooth, so you can't accidentally over-tighten them and crack the glass, which would make me very sad. Okay, now we can actually test it on the engine and make sure that they function in situ. So I got a decent oil level there in both, and you can see as the crosshead passes over that opening, the surface tension is actually pulling oil out of that pipe, and then the weight of the oil in the oilers refills the pipe. So that is working extremely well. There's a nice film of oil on there that's come entirely from those oilers. That seems to be working really, really well. I also left the oilers set up like this overnight and made sure that they drained themselves completely just based on gravity alone, and they did, so everything seems to be working very well here. Then after all that work, I realized I need oilers for the main bearings also, and the same ones would fit. So I made 2 more. These are exactly the same, except they have a different thread on the bottom and no plumbing to thread directly into the main bearings. And there's a shot of all 4. Well, there you go. This was a fun little deviation from the plans on this casting kit. I'm pretty happy with the result. I hope you agree that it is cool. And that's it for this video. I hope you enjoyed watching me make these little oilers. Thanks to my patrons for making this content possible. And I'll see you next time.